All right, so we are recording. So thank you to everyone who has joined in for this, what we're just calling a pop-up session. Kind of gets at the idea, it's certainly not something that's impromptu, but just kind of some additional programming as a part of the Summer Institute. And so what we're looking at today are some of the more practical elements of conducting data analyses. So definitely dovetails very closely with what we did on Monday, talking about some of these more conceptual ideas about using quantitative analyses to study questions related to policy. And so certainly not the only method, but it is a very useful one to have in your toolkit, so to speak, whether you're using it, whether you are working with others as a collaborator and they're more quantitatively oriented. That way you can know what the heck they're talking about. But also, and this might be the biggest one, is reading research that uses quantitative methods. So to be able to know what they're doing, to recognize strengths of that, recognize limitations of that. We are always basing what we're doing off of what others have done. And so it's really important to be able to understand at least the generalities, if not, the super specific details of what they're doing and what conclusions they're drawing. So yeah, we'll go ahead and then jump right into the presentation that we have today. So this is a mixture of, so I do have a PowerPoint that I put together, just to create a little bit of structure. Assuming that technology works, I also want to share my screen and show you in real time as I'm conducting an analysis, so you can get a sense of what that looks like. And that way you don't just have to take my word when I'm showing you some results. All right. Are there any questions or thoughts before we get started? All right, doesn't look like it, so I'm going to share my screen. All right, so hopefully y'all can see that. Get everything adjusted. All right, so I wanted to start with sort of situating what we're doing here in the broader project of what's called normal science. And so this is something that I'd referred to a couple weeks ago. I mentioned a book by Thomas Kuhn called The Structure of Scientific Revolutions. And he draws a contrast between when we're looking at what scholarly communities are doing, disciplines of researchers that are interested in the same sorts of questions. He draws a contrast between what's called normal science and what's called revolutionary science. And revolutionary science is accompanied by what are called paradigm shifts. And so this is some of the most, dramatic, maybe the most interesting from the sociological perspective of communities of scientists, but really, it's unusual. And it's certainly not something that I'm expecting, any of us to be doing here of, shifting the paradigm. Most of what we're going to be doing is contributing to normal science. And so here's a definition from Kuhn's own writing. Again, that book is called The Structure of Scientific Revolutions. I recommend anyone picking up a copy. It's pretty easy to read, pretty accessible, and it's pretty fascinating. So I think everyone would find something useful from it. So yeah, so what I want to then think about is when we look at different sorts of methods and different sorts of data and how they might contribute to this project of normal science. Obviously, we're going to be looking at quantitative methods today, and we're going to be looking at especially secondary data. So what does it mean when we're using secondary data as opposed to primary data?
This isn't like if this primary data, it's like sought out or taken in for whatever reason, and you're doing it and with whatever goal. And secondary data is looking at that information, which could still factually be true, but you were not the gatherer of said information.
Excellent. Yeah. So primary, you were the person that gathered it. You came up with the plan for why you gathered that data from those particular observations. It was very much tailored towards your specific purpose. And so we don't have to gather data anew. That would be terribly inefficient if every time we wanted to test a hypothesis that we had to go out and gather new data. But we do want to recognize that there are limitations and risks to using secondary data, even if it is tremendously common and normal science benefits from secondary data analyses. So some of the questions then that I want to think about. So if we're thinking about a distinction between primary and secondary data, experimental data versus what we would call observational data. So what would be a difference between experimental and observational data?
Experimental like focuses on like cause and effect, and it's in like an experimental setting, whereas observational, you're sort of observing, well, I guess, observing things in their natural environment and trying to like see how that behavior interacts with just normally.
Outstanding. And so when we think about experimental data, we might think about sort of stereotypically, we're in a lab. Doesn't have to be in a lab, but it's helpful to think about it that way because we have a great deal of control over what we're doing. Obviously, if we're conducting the experiment, we are generating primary data. Versus if we're using observational data, I'm not going to say that we're Jane Goodall out there, observing gorillas, what have you. We can do this for all different sorts of social science circumstances, but we are recording what we're observing. We are not directly manipulating anything to try to get at, Cadell, you mentioned cause and effect. We have less leverage over cause and effect when we're looking at observational data. We want to look at it in its natural circumstance. Okay, so if we look at then experimental data, and Cadell, I really like that you brought up causality as being something that's often associated with experimental data, because if we want to get at a causal question, we really want to tread carefully if we're not using experimental data. Some would even say that if we are doing experimental data, but we're studying people, given the sheer complexity of human beings, it's still precarious to use any sort of causal language. But to the extent that we want to get as close to that as possible, experimental data is setting that ideal. Okay, so if I've been, trashing observational data, and I should say I use observational data, so I think it's really valuable. What are some of the advantages for normal science if we're using secondary observational data? We're not gathering it ourselves, we're not manipulating it. How does science benefit from analyses using that sort of data?
If there were any bias in the data collection steps, I can imagine that if you're using someone else's, that you obviously can't have any bias towards how it was collected or whatever methods were used for that.
Outstanding. Yeah. So when the way that we've been describing it, the experiment and primary, you designed it, but human beings have biases. Even when we have groups of people, the risk of bias might be greater if we have groupthink that's taking place. And it's wonderful to be inspired by your peers and your colleagues, but there are risks that are associated with that. And if we want to have a really robust normal science, then we can see that if what's true from an experiment is also true from this larger data set that was gathered in a different context, we can say that the results from that experimental analysis generalize to other contexts. Okay, and so you've maybe heard of internal versus external validity. Internal validity means that we have a strong basis for making those causal arguments. External validity means that what is true, that a conclusion, a result applies in multiple different contexts. So both of these are good things, and to the extent that normal science as a whole has strong evidence of internal validity and external validity, our normal science is robust. It's in a very good spot. Okay, so any questions, any thoughts about this? All right, excellent. So I'm going to be focusing especially on secondary data analysis here, observational. data, although a lot of what I'm saying is true if you had your own experimental data set. But I really wanted to sort of tackle this from a perspective that I'm sure many of you would come from. And I would in fact encourage you to think about finding secondary data that might be out there that is applicable to topics that you're interested in. Even if you're in a lab and you're collecting experimental data, it's certainly not going to hurt to know if there's secondary data that's out there and to be able to use it. Data sharing is something that's really common in the sciences. I guess I should say, in my experience, I benefited as a graduate student from probably at least 2 or 3 different people that shared their data with me. And I was able to conduct original research using this data that they had, that other people had collected, and they were all too willing to share it with me. People are generally pretty excited when someone's interested in the same thing as them. So I would encourage you to not be shy about that, because most of the time people are going to be really nice and share that data, and you might get a paper out of it. You might get an interesting project out of it, and you'll never know unless you seek that out. So just a little bit of advice from me to you. In my experience, it's been pretty easy to find rich, robust sources of secondary data. Okay, so there is though a trade-off associated with this. And so like we said, I didn't gather those data. I was a beneficiary, but I need to not assume that everything is sort of 100% okay for whatever I want to do with that data. When we have really complex sources, that's, whatever that person was doing to try to record what they're interested in, I shouldn't assume that I can just open up those data in Excel, much less in Stata, R, SPSS, what have you, and assume that I'm instantly going to be able to hit the ground running. If you're doing that, you're probably going to make mistakes, make faulty inferences. So really, before you start conducting those analyses, you want to seek out what's called a code book. Alternatively, it might be called documentation, data dictionary. There might be other terms out there, but these are some of the most common ones. And so, find this. If you have a data set, but you don't have some form of documentation, I would really caution against forming certain conclusions from using those data. If you can't validate what that researcher did to create those data, there's a risk that it's worse than useless, because you might learn something that is severely misleading. Okay, so again, not saying don't use it, but make sure you have that sort of transparency from what those numbers represent. Okay, so talking then just a little bit about code books. I'd mentioned code books on Monday as being something that's really important to look at. And so when you open up this documentation, what sorts of things are you going to see, and how do you make sense of that information? So I want to show you an example of what might be a misleading item in a code book if you were just looking at it, just kind of trying to do it really quickly, and just trying to jump right into the analysis. So let me move these boxes. There we go. So this is from a data set that is called the Supreme Court Database. I mentioned this on Monday as well. This is a database that any of you could access incredibly easy. Just Google Supreme Court Database. They've got the data that you can freely download. They've got the code book right up there on the website. And so generally this is a database. What it's interested in is explaining Supreme Court justice behavior and various attributes of Supreme Court cases. And so naturally we would think all of these cases aren't equal to each other. If any of you are like me and you're Supreme Court junkies, this is Christmas is what's happening right now. We've seen big cases decided about the Electoral College, about Title VII, about abortion. It's been crazy. It's been so much that's been coming down, really interesting stuff. So I won't belabor that though, because I know I'm a nerd and I could probably go forever about that. But something that I think most people that look at the Supreme Court, I'm mentioning some of these different issues. Well, can we look at all of the cases that are decided by the Supreme Court and to assign a categorization scheme to each and every one of those cases. So pretty intuitive variable that we would want to gather. So how the Supreme Court database does this, and so you can see this in this red box that says values, we see criminal procedure, civil rights, First Amendment, et cetera, et cetera, et cetera. So makes sense. All of these are going to be different categories. They're mutually exclusive, they're exhaustive, excellent for looking at a variable. What's tricky is if we look at these numbers, 1 through 14. And so if we just downloaded this data set and we opened it up and we saw, all right, under issue area, here's a 1, here's a 3, here's a 7. And we thought, hey, this sounds interval. You know, these are numbers, these sound very precise. If we look, though, at the difference between federal taxation and criminal procedure, we can't say that taxation is more of something than criminal procedure. So in some ways, it's very misleading that these have numbers associated with it, and any sort of conclusion that we tried to draw would, at best, not make sense based off of a numerical interpretation. All right, so I'm going to slow down for a second there. Are there any questions about code books or how you might interpret some of the information contained in them?
Are they usually just included with the data set? Like if you were to purchase a data set, does the code book come with that?
I would say that they should be. And if they're not, you should be skeptical about those data. There's a very strong convention that's based off of transparency and replicability of including an explanation for what those items, you know, if you opened that in Excel and you saw rows that talked about observations and columns that were variables, if you don't know what the heck those, what's in those cells represents, or if you have to guess, I would not trust those data. Especially if you bought it. the buyer beware, I guess, there. But if you ever find a data set and you can't find the documentation, try to find out who gathered those data, reach out to them and get that code book rather than assuming that you can figure it out on your own. I think anyone who has opened a data set that someone else gathered in, if you open it up in Excel, there's probably going to be some confusing things in there, and you need this almost like a Rosetta Stone, if you will, to help you translate what that information means. All right, good questions, though. Any other questions or thoughts? All right, so I want to talk about just a couple other things to think about when you're using someone else's data before we get into some of the more nuts and bolts of conducting data analysis. Let me bounce back there, sorry. All right, so very often you're going to have missing data in a data set. Just talking from examples, so we've talked about the SIM data set. This was a data set of a few thousand Iowans, asking them all different sorts of questions about health habits, you know, dental, mental health, access to food resources. And so not all of these are sensitive questions, but some of these, especially we might think with mental health, those are pretty sensitive questions. And so even if the person gathering the data, you know, calling people up on the phone, they might be a very trusting person, but some people just aren't going to answer that and they might just skip it. And so the result would be is that we don't just want to throw out any response that we have from that person about those other items, but we might then have some sort of convention about, for these mental health items, this person didn't respond. So when I say a convention, sometimes this means, here I say like NA, this means not answered or not applicable. Sometimes it's a 99, which I don't really know where that comes from, but if we have sort of 1, 2, 3, 4, and then you have 99, that is really going to confuse your software. And so you want to know if there's missing data, and if it's coded as an NA or a 99, you know, you're obviously not going to want to analyze those in the same way as people that did respond in a way that, you know, fits your coding scheme. All right, so missing data, you can't do a whole lot about that, but you absolutely want to know if it's there and make sure that your statistical software of choice is accommodating those missing values. I can talk more about that if people want as well, kind of their strategies for, it's called imputation, for imputing what you think the value might be for people that didn't respond. That's risky, but it also means that you are growing your data set. All things considered, it's better to have more data than less data. Okay, so the final thing that I'd recommend that you look at in the code book, so know what the numbers represent, know if you have missing data, know if there is what's called weighting or pre-processing that is required of those data before you can analyze them. So like the word pre-process suggests, this is something that you have to do to the data before you can actually analyze them and make sense of them. So sometimes these are to make sure that you're comparing like with like. Again, I won't go too far down that road unless people want to, but this is pretty common in research to have it be pre-processed. Weighting is pretty common in survey data, especially if you are trying to represent the population. And so as we saw in the study that we read for Monday, that the sample skewed older, it skewed more towards female respondents. Oftentimes we'll see that it skews in terms of income. And so occasionally if you see that, we don't need to throw those data out just because they don't look exactly like the population. What we do is we want to properly weight those respondents that we have. And so if we have only, a handful of people that are of a particular race or ethnicity, or just check a number of boxes, we're going to weight them so their values, their responses reflect the true demographics in the population, basically. All
So
right.
with that, just a quick question, with that, the weighting, if you're just looking at the demographics, like would you just take in Iowa, I think it's like 97% white. So would you just take that number and use that to just try and get it as close to that with the data?
Yeah, so it's not quite 97%. It's close though. I think it's like 90 to 93. It's still not good though. But yeah, so then that's a good example, because if we're looking at questions related to people's attitudes, you're going to see breakdowns based off of race. People of different races and ethnicities are going to have different views. And so what the weighting then is going to do is to essentially put a multiplier, if you will, on people in underrepresented groups to try to get that to reflect it, because we don't want to have it be, well, you might want to, because maybe you're really interested in the views of, say, African Americans, and you might then oversample on that group, and so get essentially your population is African Americans rather than all Iowans, and so that might reflect what's called your sampling frame. You do want to be careful though, is that if you're really interested in the views of African Americans and you have a sample that is 1,000 people and you have 3 African Americans in it, you don't just want to put a huge weight or multiplier on that, because there's a lot of random error associated with that, and those 3 people might be very unusual. We'll put that kindly. And generally when we have larger numbers, the views of any one person matter less. And so we want to kind of keep that in consideration, to have sort of a rough baseline number of people, and we're not just only relying on weighting. Great questions though. And so really just wanted to drive home that an important prerequisite to doing any sort of data analysis is spending quality time with the documentation. And I realize that that probably sounds incredibly unexciting, but if you want to do data analysis, don't just assume you know what those data represent until you do some of this homework. All right. So let's start then moving towards the more practical. orientation. So what we're going to discuss here is assuming that you have, done your homework with the code book. How are we going to think about using the statistical software to describe these variables? So we're going to focus pretty heavily here on descriptive statistics. And talking about the distribution of a variable, and we'll get a little bit into visualization as well. I'm going to be using a statistical software package that's called Stata. Has anyone used Stata before? Okay. Seen a few hands. What other statistical packages have people used?
I've used SPSS.
Okay, great. I know someone said that they used R on Monday, and I was impressed with that because R's a beast. R's great, but R's hard. All right. So Stata, SPSS, R, even some of these things you can do in Excel. Generally, what I'm going to be saying about Stata applies it's pretty true of other statistical packages as well. I chose Stata because that's usually what I use. I will use R though occasionally for visualization. It's got some great packages for how you can present your data more clearly. Stata doesn't do as well with that. All right, so we're going to look at some visualization. We're going to look at some description. So if we have loaded our data into Stata, we want to start thinking about the distribution of an individual variable. So I'm going to talk about one variable distribution, and then I'm going to talk about what are called joint distributions that look at the patterns between two variables. Okay, so before I pull up Stata, I just want to talk a little bit about when we think about what a distribution looks like, to give you a way of thinking about that visually. Okay, so what we want to do is we want to think about horizontally, talking about the different values that a given variable can take on. And so if you think about something like age, we have 0 to a few people that are older than 100. And so we would start at the left and then essentially have a different tick mark for those different categories that we're looking at. If we're looking at something that is a binary dummy variable, it's going to have 2 categories. If we're going to look at something though like age, and we want to look at each individual year, then we could have 100 some categories. That is up to you in terms of how you want to measure that. This is called precision in measures. Generally, it is preferable to have more precise measures than less. But if you have some pretty sparsely populated categories, then you might find yourself collapsing those, making your measures less precise. We actually saw this in the study from Monday. If you remember that measure of satisfaction with your dental insurance, it had been from 0 to 10. They wound up collapsing it. 0 to 6 was one category, 7 to 10 was another category. So they had very good reasons for that. Plenty of people do that. Okay, so when we're thinking then about visualization, the convention is generally it's horizontal, left to right, putting those different categories. Okay, so when we're creating what's called a frequency distribution, we're not just going to be horizontal, we'll be vertical as well. So we're using 2D. And so you want to then look at, within your sample, how many observations are in each of those categories. All right, and so if we, using that example of the Reynolds study from Monday, they found that a lot of people skewed high. And so if we then had going vertical, we would see a lot of people that marked 10, versus if we looked at probably 1 or 2, I would imagine people are probably either they love their insurance or they hate it. They're probably not like, I'm going to give it a 2. I don't like it, but I don't absolutely hate it. Who knows though? But we're going to see this by plotting this, and we're going to get a sense, all right, do we have a uniform distribution where it is flat all the way across? Do we have what's called a normal distribution where we see kind of this nice appealing bell curve? This is going to be something though that we want to look at with the frequency distribution, something that's going to tell us. Okay, So my question for you, now that I've described kind of in general when we're talking about a frequency distribution, what information would you be curious about finding out about what that variable actually looks like? What are some desirable things about a distribution? You know, you see that and it's like, ah, this looks great. What are some bad things that you see that and you're like, oh, I might need to, you know, measure this differently? All right. So I mentioned the normal distribution just a moment ago. Can anyone tell me what is a desirable characteristic of the normal distribution?
That it kind of matches like a standardized like bell curve.
Good, good. So it looks like a bell. Can you elaborate on that a little bit? Like what gives it its bell-like shape?
I guess like having that uniform, well, not uniform, but like where it matches the standard deviations and like the different percentages in each category.
Yes, so excellent. So when we talk about standard deviation, this is a measure of dispersion, how spread out our data are. If we had a sample that was 100 10-year-olds, I don't know where I'm coming from with that, but everyone was the exact same age, we would have no dispersion. We would have a mean of 10 and we would have a standard deviation of 0. If we though had a different sample that still had that mean of 10, but we had some people that were 9, that were 5, we had one weird 50-year-old in there, we would have a lot of dispersion, and standard deviation would be an important way of talking about what that sample actually looks like. And so if we have a variable that is normally distributed, we know a lot about that standard deviation. So I'm going to come back to that point in just a moment after I show you what a normal distribution looks like. Okay, so I should say these are fake data. These don't actually represent any specific sample. I used data and I told it to create a normal curve. And so I'm just showing it to you now so we can see, you know, as Cadell mentioned, that appealing bell shape, that it starts small and then slowly increases. The highest point is right there in the middle. And then we see that it tapers off in the other direction. So might not look like a bell to you, but this is described as a bell curve. The defining characteristics of the normal distribution is that you see that the highest points for this distribution, because again, looking at the bottom, we see that horizontally, these are the different values that the variable can take. Along the y-axis, these are the number of observations in each category. And so if we look at this normal curve, the category that has the most observations is the same thing as the mean. All right, and so remember that the mean, this is the typical value. If we had to assume something about a random observation in our sample, we would say, all right, the value that they're most likely to have is whatever that mean is. Okay, so another characteristic then of the bell curve is that it is symmetric. So if we were to print this out and we were to fold it in half along the mean, then what is to the left of it is very similar to what is to the right of it. And so a perfect normal curve would have that be entirely symmetric. It would be a mirror image of it. Okay, and so then the final characteristic is that we see, you have to look really, really closely, but say if you look to the left of that -4, you can see that there's an observation there. And so again, these are randomly generated, but when we see a normal curve, that this is going to be asymptotic. So it approaches 0, but there can be, say, height is a variable that's normally distributed. You have the Yao Mings of the world, and then you have people that are also really, really short. Most people are going to cluster around that average, but you're going to have some really high and some really low. All right, so then bringing this back to what Cadell said about the standard deviation, if we have a distribution that is normally distributed, then we can say with confidence that this percentage of our sample lie within 2 standard deviations. This percentage lie within 2 standard, this percentage lie within 2 standard deviations, 3 standard deviations, et cetera, et cetera. We couldn't say that with that same degree of confidence if we had a non-normal distribution. All right, everyone with me? Any questions? All right, so let me show you where this came from. So I'm going to use as an example in Stata. As I mentioned on Monday, I'm a big fan of using baseball to demonstrate quantitative features and to use statistical software. So I'm going to show using Stata some different analyses that you can do on a sample of baseball players, just to give you a sense of what this sample is. This is anyone in the 2009 season who had at least 100 at-bats. So we're not likely to have really any pitchers in here. You know, they're not getting 100 at bats. So we have kind of a baseline level there. People that are regularly having opportunities and what that looks like. So it kind of looks normal. It's not quite there, but we see that, you know, you have a lot of clustering, you have kind of decreases and increases. So it approaches normal, but this is kind of more interesting of a distribution than that normal distribution. So you have some truly lousy hitters down here. Any baseball people know that if you've got someone on your fantasy team and they're hitting 150, they better be a really good catcher is probably what it is, and be making up their value elsewhere, versus if you have someone hitting 350, you know, that they are getting a hit almost more than every third time at bat. All right, so I'm going to change my screen to look at a different one. If I have the right one. There we go. All right. So I'm showing you now, you should all be able to see my screen for using Stata. So you can see my desktop. I have a couple things here, and I wanted to show you something first, which was this data set that I showed you, the distribution of batting average. I think it's really useful, though, first to look at what it looks like in Excel. And so this is, again, from 2009, any baseball player that had at least 100 at-bats. You can see in this column A, this is the person's name, B, their team, C, their league, D, batting average, E, at-bats, F, hits. So nice mixture of variables here. Team and league, these are nominal. These are different categories versus batting average, at-bats, hits. These would all be interval. And so recall that interval, this is really informative. This means that not only can we say that some people rank higher, but we can say with a great deal of precision, the difference between someone that bats 202 and 203, that difference is identical to someone that bats 302 and 303. Okay, so this is then what the data look like in Excel. So I'm gonna exit out of that. And I'm gonna open that up in Stata. All right, so this is what Stata looks like when you open it up. Not very attractive. Some statistical packages are quite a bit more attractive. So if you're going for aesthetics alone, Stata is pretty homely. So I'm going to open up then that same data set, and I'm going to do this using the import feature. And so Stata can accommodate a number of different data formats. You can see that I can put Excel spreadsheets in there. I can put in what's called a CSV file. It's called a comma delimited format, or a delimited format. You see that it can read SAS, so SAS. Some people might use that. It can actually read SPSS format into it. So it can read data sets that are proprietary to other software. So if you can download it online, Stata probably can read it. All right, so I'm going to click on the CSV, go to Browse. So here then on my desktop, I'm going to click on batting averages. That's the one that I just opened. I'm going to click OK, and boom. So it is now in Stata. We've seen it change a little bit. Here on the right side, you can see all of these variables that we saw in Excel are now in Stata. Okay, So this box down here, this command box, this is where I type in the code, if you will, and I tell Stata what to do. Stata does also have these drop-down commands, so things like file, edit, data, what have you. Some of you might be more comfortable using those drop-downs. That's a matter of personal preference. You can also see that on the left side that this keeps track of each of the commands that I've done. So this import delimited, that was when I told Stata, these are the data I want to look at. All right, so the first command I want to look at is something that is very intuitively called codebook. And so we know what a codebook is. It tells us information about the variables. In Stata, it also tells us some useful descriptive statistics. So let me jump up to this variable at bats. So this big box here, this is where it tells me the results of my analysis. So I told Stata, do the codebook command, and this is where it gives the output for that. So it has a variable called at bats. We can look at some of the information that it provides. So it tells me it's a numeric variable. Some only have 100 at bats, some have many hundreds. You can see the range here from 101 to 682. So thinking then about our distribution, it would range from 101 all the way to 682 horizontally. Okay. A lot of different information here. It tells us the mean, tells us the standard deviation. So the typical value would be about 342 at bats with a dispersion of 164. So pretty significant standard deviation. All right, is everyone with me so far? Can't see everyone as well, so I hope that no one has eyes glazed over. All right. So let me get some more code here. So I want to show you then how I created that distribution of batting average. Okay. So I'm going to tell Stata to create what's called a histogram. So the command is HIST. I'm going to do this with batting average. So the name of the variable is batting AVG. And then I include at the end FREQ. That tells me that I want the histogram in terms of frequency. Okay, so Stata's thinking. There we go. So hopefully you can all then see that distribution that is identical to what had been in the PowerPoint slide. All right, so I'm going to bounce back to that PowerPoint then. That's not what I want. Where'd it go? All right. There, now I can see people again. I was a little worried that it was just me talking to myself. I've had that happen before where the internet basically went down and obviously no one could tell me that I was talking to myself. So reassuring. Okay, so what we saw then was, let me bounce back to that, what's called a frequency distribution. And so it tells us then our values of our independent variable. These are different batting averages, and it tells us how many people fall into these different categories. We might find it useful to express it as a relative frequency distribution, where rather than just having that raw number along the y-axis, we have a percentage. And so the value of this is that the percentage aids interpretation. We might hear that there are 7 people who have a batting average greater than 340, but if we can't put that 7 in context with how many people are actually in our sample, that's not very useful. But if we can say that that is 2% of our sample, that's a lot easier to interpret and to explain to other people. Okay, so we're not changing the underlying information. We're just using some pretty basic math to be able to determine that relative frequency. So what you do is that if you're looking for the relative frequency of a given value, I'm going to do this for players that hit at least 350. So that's all these people out here in this far tail. I want to look at the percentage of people that hit 350 or more. Okay, so we would guess that it's pretty small. So what I would do is that I would, if I wanted to do this by hand, I can also tell the computer to do it. I'm going to divide the number of group members that meet that criteria, so 350 or above. I'm going to divide that by the overall size of the population. So there's the relative aspect of the frequency distribution. This is going to give me a decimal. So if I multiply that by 100, then I will get a very straightforward percentage to compute. All right, so I did this for people that meet this criteria. There were 4 people in that sample who hit 350 or above. There are 446 total major league players that are in my sample. And so 4 divided by 446 multiplied by 100, this gives me 0.19%. So if I just said 4 players did it, some of you that might mean something to, but you're probably a pretty big baseball nerd. If I told you, though, that only 0.19% of major league players hit this, then everyone can understand, wow, that is truly impressive and very rare. So I could also then tell Stata to create a relative frequency distribution. This looks pretty similar to the regular frequency distribution. The only difference here is the percent, and that makes it very intuitive. So I can say, all right, here, this is the highest column. This is where the most hitters are at. And I would say that that is roughly, a little bit more than 10% of my sample fall into that category. All right. Any questions, any thoughts? Right. So the code for this is very simple. You would be able to create a frequency distribution, a relative frequency distribution. If you want to use Stata, you do have access to this free as Iowan students. It's a little tricky to access, so let me know if you need some help with this. I would recommend, though, Googling University of Iowa Stata. You're going to be able to use the network to be able to access this. It's something that I've done. Again, it's a little arduous, but might be worth it. All right, so the final thing that I want to talk about today, and so again, we're really just scratching the surface, but I wanted to set some reasonable objectives for beginning data analysis. And so looking at single variable distributions is a great place to start. Looking at what's called joint distributions is a natural progression from there. Okay, and so then this helps us learn about the relationship between 2 variables. We're essentially going to plot the values of one variable along our x-axis and a second variable along our y-axis is going to be what it looks like. And so a common tool for looking at the joint distribution is what's called a scatter plot. We saw some scatter plots on Monday, and I'm going to show you how to create those in Stata. All right, so by looking at a scatter plot of 2 interval level variables, so again, the most precise, where we see something like income, age, batting average, speed, where there's ranking makes sense and we can make very fine distinctions between those categories. When we can do this, we can plot it on a scatter plot, we can say something about the correlation. When we do this, a correlation tells us the direction of the relationship as well as the strength of the relationship. So we saw this figure on Monday that shows a positive relationship. So as our independent variable, as our x variable increases, our y variable also increases. A negative relationship, as that increases, our y variable decreases, and then no relationship just kind of looks like chickenpox. Knowing the value of an independent variable tells us very little, if nothing, about our dependent variables. You can especially see that with this value of the x variable. You see a low value, some intermediate values, and a high value. If we saw this, we wouldn't have anything to analyze going forward. And so that's why we start by looking at things like scatter plots, because if we see no relationship, no amount of regression is going to unearth a relationship there. So that's why we start with this. All right. So I'm going to show you how to create this in just a moment, but this is an example of a scatter plot using that same baseball data set. What I did here is I told Stata to create a scatter plot between at-bats and batting average. So at-bats, this is essentially, you get a hit, you reach on an error, you reach on not on a sacrifice. So this is generally, if you're a baseball person, if you're not a baseball person, at bats is frequently when we talk about, that is going to be most of the time when you're at the plate, that it is going to result in an at bats. Okay. So this then says for each of those 400 some players, everyone is going to have a value of the number of at bats that they had in a season. Recall that we said this had to be more than 100. So that's why we have this pretty stark line here. We have some people that are way out here that are getting more than 650 at-bats. Right? So that's one variable. And here I just want to relate that to batting average. And so I did this just, I would expect a positive relationship, and that's what I see here. Scatter plot tells us the direction, so as at-bats increases, so does batting average. It also, though, gives us a sense of the strength. And so I'm just going to ask you guys, if a positive correlation can range from 0 to 1, and 1 would be a perfect line, all of these were just essentially on top of each other, what would you think the correlation is here from 0 to 1? What's to hazard a guess?
0.3.
Okay, we've got a 0.3. So generally 0.7 is what we're looking for. 0.7 is a cutoff for a strong correlation. We've got a guess at 0.3, which is actually pretty close. This is 0.47. So it is a positive relationship, but it's a weak positive relationship. All right, so here we have a little different scatter plot. And so this looks at hits versus batting average. Again, a positive relationship. What do you think, though? What would you guess if this is higher than 0.47? Do you think this qualifies as a strong relationship?
Probably not a strong relationship, maybe like a 0.46. I don't know. It's getting there.
0.46, very precise. It's not
0.6. I meant 0.6.
Oh, 0.6. Very good guess. So yeah, it's not quite strong. This is actually 0.62. So good job eyeballing that, which we kind of can. I mean, if you look at enough of these scatter plots, you might not be able to do it exactly, although that might be a good party trick or, I don't know, carnival trick. Guess my correlation. I don't know, maybe I'm a nerd and that's why I think that's funny. But yeah, you kind of get some experience then about what those different correlations look like. All right, so that's hits and batting average. We would expect those to be related. And then here we see the strongest correlation. So like I said, if it was a 1, they would all be stacked on top of each other. And this is pretty darn close to that. And it looks at at-bats versus hits. I won't get too far into it, but most of the time, if you have an at-bat, and it would be like a hit, it would be an out, it would be an error. So generally we would think that there would be a very strong conceptual relationship between hits and at-bats because they're almost the same thing. So if you're having more at-bats, you're gonna have more hits. So not quite 1. This is 0.97 is what this correlation is. So again, if you see this looks really good. All right, so let me get back to Stata.
Where did that number of 0.7 come from to determine if it's a strong relationship or not?
So that's, as far as I know, where it came from. It's just a convention among scholars. There is a similar convention when you're looking at statistical significance, which is something in regression and other tests of 0.05. And so naturally we could quibble with it. And I'm sure there are some good reasons for it, but ultimately it's a cutoff point that is useful for talking about kind of distinguishing what is a really strong relationship versus something that not quite as interesting. All right, so let me get back to Stata. All right, can you all see Stata now? Is that what is on the screen? Hopefully. Okay, so let me then show you how to, what commands to write to create a scatter plot. Nice thing about Stata is that it's pretty straightforward, so the data are already loaded in. The command is called scatter. Then you want to type the two variables that you're interested in. So I've got batting average and at bats. So I'm going to go ahead and do that and click enter. So here then is the scatter plot that we saw before. I can also run the command that is the correlation command. And so I'm going to do this for batting average and at bats. I do that and it gives me the statistic of 0.47. So that's where I was getting those numbers. Let me show you then. So we see for hits and at bats. So scatter, hits, at bats. And that is where, again, it's almost a straight line. I can type correlation hits at bats, and that's where I get that 0.97. So it's actually 0.98. So I should have gone out another decimal point there. So incredibly strong correlation. All right. So again, we're just scratching the surface in terms of what Stata can do. So I'm going to go ahead and stop sharing my screen. All right. Yeah, so we're just scratching the surface on what Stata can do. I wanted to show you, though, how to start using statistical software. And so things like inspecting your data in either Excel, SQL, you might just decide to inspect it in the statistical software itself, is something that you can literally eyeball it and just see what those values look like. I also recommend then looking at the code book, so knowing what those numbers represent, because I want to be very careful with that. I could have just gone into Stata and start typing commands, and I might come up with some interesting results just by chance. But we want to be principled with how we use statistical software. Because if we don't, we might come up with results, but if it's not grounded in our understanding of that topic, then we have some pretty pejorative names for what this is called. Sometimes it's called pea hunting, stargazing. All of these are in reference to, we might find what's called a statistically significant result, but it doesn't have a whole lot of meaning to it because we were just fishing for numbers. Statistical software makes that really easy to use, and I want to caution you against doing that. So that is a statistical no-no, so don't do that. But if you've got a really interesting question to look at, I recommend starting with looking at the distribution of those individual variables, looking at the scatter plot, so how they relate to each other, because if I had done that and I had no relationship, then I would probably just stop there, because again, the more complicated tests, things like regression, things like chi-square tests, that they depend on, there being some relationship that no amount of statistical manipulation is going to change. Because the computer is just telling us the statistical relationship that's there. It is up to us to ascribe meaning to it. So that's kind of where I want to leave off with here. There's a lot more that you can do with statistical software, but these are some really valuable first steps that you can take. All right. So are there any questions, comments, things that people want to talk about from today's pop-up?
If we wanted to download like Stata, is it through workflow that you have?
It might be. I will go ahead and defer that question. I'm going to see if there's any other questions before that, and then we can stay on and I can help you figure out how to download it if you want to.
I would just say real quick, if I use a Mac and I use Citrix Workspace, then that works really well. And you can get Stata through that. We use it in public health. So.
Yeah, and that's what I'm going to do. Yeah, if you access the network, and then you can essentially tap into another computer, like a virtual computer that has Stata downloaded to it, is what you can do. All right. Any other questions? Well, thank you to everyone for joining. I thought this went really well, and so hopefully, you've learned a thing or two. Even those of you that have some experience with statistical software, I know for me, it's always really useful to just like return to some of the basics, because it's easy to just open up software and to just start hitting buttons. But we want to make sure that we have our fundamentals sound, and that was what I wanted to demonstrate today, was how to make sure your fundamentals are sound before you then move to the next step, which would be conducting statistical tests. All right, well, that wraps it up. Liam, if you want to stay on, anyone else who wants to stay on, we can talk a little bit about how to access Stata on your own.